This video is on vectors and types of measurements with vectors. It's to help better illustrate how we represent vectors and how we add them together, and how we use component vectors to establish x and y relationships for angled vectors. First, let's review the two types of quantities that we measure in physics. Scalar quantities is the first one. These are measurements that have magnitude only, like mass, distance, temperature, volume, speed. None of these have a directional value. They can be the same in any instance. If I walk 5 miles, it doesn't matter what I'm talking about for distance. 5 miles could be 5 miles in a circle, could be 5 miles in a straight line. It's still a distance measurement. If I have 5 kilograms, it's the same on Earth as it is on the moon. Okay, so none of these have a directional value to them. And just a couple of reminders of distance being total length of a path traveled, and speed is distance over time. Vector quantities were quantities that now had magnitude and a direction, such as displacement, velocity, and acceleration that we learned about in Unit 1. Displacement was the distance from point A to point B in a straight line with a direction. Velocity was speed with a direction, and acceleration was the rate at which velocity changes over time, either speed or the direction part of velocity. So vector quantities have a direction and a magnitude, and we're going to show how to represent that. A vector is simply shown on paper as an arrow. An arrow tells you a couple of things. It points in a direction, and the length of the arrow can mean something. The magnitude of the vector is shown by the length of the arrow. So for instance, we have a 1 meter vector, which is let's say this was 1 meter long, and a 5 meter vector that is 1, 2, 3, 4, 5-ish meters long. So the magnitude of the vector, of the arrow, can tell us about the vector. Also, the direction that the arrow is pointing tells us the direction of the vector. And this is useful especially for making angles with the x-axis or with the y-axis. For instance, this is east, northeast. This you could consider to be maybe this is a 45-degree angle, maybe not, but it still helps us establish direction. Vector translation is also a helpful tool for us when we're adding and subtracting vectors together. A vector can be moved anywhere you want on the page as long as you maintain its direction and its magnitude. It's still the same vector. So in this instance, A and B, even though they're at different spots on the page, A and B have the same direction, or you could say the same angle with the x-axis. They've got the same angle. And they've also got the same magnitude, the same length. So A and B are the same vector, basically. Vector addition occurs when you add two vectors together. It's kind of like taking all of the directions that you travel in multiple different directions for a path and adding them all together to give you a point A to point B line. This final line, the addition of two vectors or three vectors or however many vectors, is called the resultant. It's the result of adding vectors together. In this case, to add these vectors together, we took vector B, we translated it down, maintaining its direction and its magnitude, so that the beginning of vector B was connected to the head of vector A. What this did was it established a path for us to follow, and the resultant of that path is vector C, going from the beginning of A to the beginning of B. We're going to see this drawn a couple different ways, especially with one of the rules that's coming up. Since vectors all have this property of maintaining direction and magnitude, you can take multiple different vectors and add them all together in multiple different ways and get the same resultant. Let's say this x that's on each of these sheets is the same point in somebody's yard, even though it looks like it's in a different spot in these three squares. That's just to fit them on the page. Let's say it's the same spot in somebody's yard. If you take vector A, B, C, D, and E and add them together, as long as you maintain the direction and magnitude, you'll get the same resultant, R, 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 for this setup. It's kind of like taking directions and putting them on note cards and just shuffling the note cards. You're going to get to the same place every single time. Think of a square. If I was to be walking a square on my lawn and I'm facing in the same direction the whole time, it doesn't matter if I walk forward and then to the right and then backward and to the left. I could go to the right, forward, to the left, and backwards and still make the same path that I have. So if you look at the first one, it goes A, B, C, D, E, and I get my resultant. The second one goes D, E, A, B, C, and I still have the same resultant. And the third one, different arrangement, same resultant. A simple way to add vectors together is the parallelogram rule, and I'm going to draw this one because it's a little more complicated, but you can translate vectors so that they form a parallelogram. For instance, if I have this vector and this vector, and I want to add them together to see what the resultant would be. Think of this like one of your friends, you're at the beginning, and one of your friends is pulling you to the right, and another one's pulling you forward. If they do it at the same time, you're going to travel both forward and to the right. But which way is it? Is it going to be more towards the top, more towards the bottom? In order to do this, what we're going to do is translate these vectors. So I'm going, oops, let's get rid of that. I'm going to take this bottom vector and I'm going to translate it up so that the beginning of it translates along the other vector to the top. And what I should get is this. I'm then going to take the vertical vector and I'm going to bring its bottom and translate it along the vector on the bottom, so I get kind of a mirror image on the other side, and I get this. And that forms a parallelogram. So this was vector A, which I translated up here, and this is vector B, which I translated over here. And the way the resultant works is I go from the beginning of both original vectors to the end of both original vectors, and that is my resultant. And that's how the parallelogram rule works. It's easy with 90-degree vectors. It becomes very helpful when you have vectors that are like this, and you have to translate them to form a more complicated resultant. Vector components is going to be a helpful tool for us, especially in the projectile motion unit, and to be honest, in units 2, 3, 4, and 5, it's going to be a very helpful tool for us. A component is part of an angled vector that the vector has to do anyway. So if I'm walking northeast, I'm walking north, I'm also walking east. Those are my components. Every vector at an angle is made out of two components, an x and a y component that are made on their axes. So if you look at this one, for example, this vector A has some x-ward motion. If I draw a vertical line down to the x-axis, it also has some y motion if I draw a parallel line over to the y-axis. So it's made up of these two parts. You can't go any farther on the x-axis than the original vector was in a 90-degree line. You can't go any higher on the y-axis than the original vector was on a 90-degree line. What this does is it helps me establish x and y components for all angled vectors. So for instance, if I have vector A, B, and C here and I want to add them together, it's difficult to do with all their angles there and the way they're oriented. But if I were to break them up into all their x and y components, then when I add them together, if I add all the x's together and all the y's together, ax, bx, and cx, and ay, by, and cy, add them all together, I get this final total x component and y component. If I draw my parallelogram rule, I get my resultant for that. So taking x and y components breaks it down into two directions that are 90 degrees to each other. And if I wanted to use this, I mean, you have an x component and a y component and a resultant at a 90 degree. That forms the Pythagorean theorem, which we can use in order to calculate what that hypotenuse would be. When we do vector components, in order to calculate what they are, we have to use trigonometry functions. If you remember your trig, your cosine of your angle equals your adjacent, which is the ax, over the hypotenuse, which is the a. And if I multiply both sides by a, I get this formula right here, ax equals a cosine theta. And that will solve for my x component. My y component is the same idea, except I'm using the sine of the angle equal to the opposite, which is ay, over the hypotenuse, which is a. And if I multiply both sides by a, I get this formula right here. Now, these aren't actually formulas. These are trigonometry equations. They could change. The sine and cosine would swap if I was to make my angle with the y-axis right here. So if I made my angle right here with the y-axis, this cosine and sine would switch places because they would no longer be adjacent and opposite the way they were with the angle made with the x-axis. So they're not actual formulas that we're going to write down, but you do need to know the relationship in that triangle. So making components like this are going to be very, very helpful for us for angled projectiles when we need to take an angled velocity and break it up into components in order to use for our equations that we'll get during this unit. Make sure you take note of this. You can refer back to this video anytime you want, especially for units 2, 3, 4, and 5, because we'll be using vector components for all of those and the ability to break these vectors up, especially unit 3. Very much so unit 3 and 4. When we get to Newton's laws and forces and momentum, we'll definitely be using vectors. So make sure you keep this handy, print it out, take notes, and remember where it is. I'll keep it in unit 2 so you know where to find it.